Welcome to day 29 of Math 111. In the lesson today, we are working with multiplication and division of fractions. We will begin with multiplication. We can model multiplication of a fraction by an integer with repeated addition. Our example here is 4 times 1/2. Remember, that's 4 copies of 1/2. So we can express it like this. We see 1/2 repeated 4 times, added together. We learned in our lesson on addition that we add the numerators when we have a common denominator. So we get 4 halves, which is equal to 2. You can model this also with things like fraction circles, fraction strips, and other sorts of manipulatives. You'll see here that I've got 4 fraction strips, and in each strip we represent 1/2. When I put these together, I see that I have filled in 2 complete fraction strips. So 4 times 1/2 is equal to 2. This is a physical representation of this multiplication problem. Let's look at what happens when we change the order of multiplication. We have 1/2 times 4. We're multiplying an integer by a fraction. This looks a little different. To model this, we consider 4 units, and we want to divide the 4 units into 2 equal parts. So I've separated the 4 circles here into 2 groups of size 2. We're multiplying by 1/2, so I select one of the 2 groups. So I see here that 1/2 of 4 is 2. Let's consider another example where we're multiplying an integer by a fraction. This time we have 3/4 times 3. I'm unable to divide 3 into 4 parts conveniently, so I'm going to divide each of the 3 units into 4 parts. So the 3 circles represent my 3 units, and I divide each circle into quarters. You can see this done in the diagram below. After I've divided the circle, I'm going to separate the parts to form an array. So the 4 parts of each circle have been separated, and I actually did them in columns. So you'll see all of the quarters there. Next, I'm going to group these up. I'm multiplying by 3/4, so I need 4 groups of equal size. These will be my rows. I've got 4 rows there. I'm looking for 3/4 times 3. So I have the 4 rows. I'm going to select 3 of those 4 rows. As we count inside the part that I've separated here, you'll see that I have 9 pieces. These are 9/4. So the product, 3/4 times 3, is equal to 9/4. You may want to think about this a little more. Think about what we did and why we had to go through this process. Next, we'll move to multiplication of a fraction by a fraction. We will use the area model for this one. We're going to think about 2/3 times 3/4. I'm going to begin with a square that is 1 unit on each side. I'm multiplying 2/3 and 3/4. In that first fraction, the denominator is 3. So I'm going to divide the vertical side here into 3 equal pieces. I'm creating 3 horizontal strips here. Right? Each of these is the same size. The second fraction, 3/4, denominator of 4 here, and so I'm going to divide a horizontal side into 4 equal pieces. So I've got these vertical strips here. I'm going back to the 2/3 now. I divided the vertical side by 3, so I have the 3 equal strips, and because I have 2/3, I'm selecting 2 of the 3 strips. I've colored them blue here in the diagram. The second fraction is 3/4. So I have the 4 vertical strips here, and I'm selecting 3 of the 4. I've colored them yellow. To form the product, I'm going to select the overlap. So where the blue strips and the yellow strips overlap, I've colored green. I can see that 2/3 times 3/4 is 6 of the total number of pieces that were in the square. So there are 12 pieces, and I've selected 6. So the product, 2/3 times 3/4, is equal to 6/12. And of course, we can simplify this fraction. This becomes 1/2 when we simplify it. Notice that in this model, we get some motivation for the way we typically multiply fractions. 2 times 3 is 6, and 3 times 4 is 12. So we're multiplying the numerators together, and we're multiplying the denominators together. Let's now look at the definition for multiplication. Let A over B and C over D be fractions, and their product is given by A over B times C over D equals AC divided by BD. Again, multiplying the numerators and multiplying the denominators. As I mentioned in the previous example, the picture gives us motivation for this definition. Before we move on to division, I want to remind you that we have looked at 3 different scenarios involving fractions. We had whole number times fraction, we had fraction times whole number, and then fraction times fraction. Each of these has a slightly different model. Make sure you understand these. Go back if you need to and review these. We'll now move on to division of fractions. We're going to use the idea of money to help motivate some of the ideas that we have when we divide fractions. We'll have several of these examples. Suppose that you walk up to a cashier with a $20 bill. You ask, how many $5 bills will you give me in exchange for $20? The answer, of course, is 4 $5 bills. This is modeling the division problem, 20 divided by 5 equals 4. Here's another one. You have a $1 bill. You ask, how many quarters will you give me in exchange for this $1 bill? Well, the answer is 4 quarters. And we know that a quarter is 1/4 of a dollar. This is modeling the division problem, 1 divided by 1/4, and the quotient is 4. Here's another one. This time we're asking about dimes. How many dimes will you give me in exchange for a $1 bill? We know that 10 dimes is equivalent to $1. So a dime is 1/10 of a dollar. The division problem that we are modeling here is 1 divided by 1/10 equals 10. Are you seeing a pattern here? Let's look at some more examples. This time we ask, how many nickels will you give me in exchange for this $1 bill? The answer is 20 nickels. In this scenario, we are modeling the division problem, 1 divided by 1/20, and the quotient is 20. Here's another one. We have a $5 bill. How many quarters will you give me in exchange for a $5 bill? Remember, a quarter is 1/4 of a dollar, so the answer is 20 quarters. Our division problem this time is 5 divided by 1/4, and the quotient is 20. Again, we have a $5 bill. This time we want to know about the number of dimes that we would receive in exchange for the $5 bill. The answer is 50 dimes. This division problem is 5 divided by 1/10 equals 50. Notice that with the coins, we're using what we call unit fractions. Starting with a $10 bill now, how many nickels will you give me in exchange for this $10 bill? The answer is 200 nickels. There are 20 nickels in a dollar, so this would be 20 times 10, or 200 nickels. The division problem that we are modeling is 10 divided by 1/20, and our quotient is 200. I hope that you were able to see the pattern as we went through those problems dealing with money. It's important to do a number of these so that students will see a pattern as they go. We have a theorem that involves formulas for the division of fractions. The first one that we have here is the common numerator rule. We have a over b divided by a over c. Notice that the numerators are the same. This is equal to c over b. So notice that we've got a quotient involving the denominators. And look at the order of these. We have the common denominator rule, a over b divided by c over b. So notice that the denominators are the same, and our quotient in this case is a over c. So look at the order of the numerators that appear in the quotient. Our third rule is invert and multiply. A over b divided by c over d is equivalent to a over b times d over c. This is probably the one that you are most familiar with. I want to bring up another definition. The reciprocal of a non-zero fraction c over d is the fraction d over c. A lot of times we talk about flipping a fraction. The correct word is forming the reciprocal. So the reciprocal of c over d is d over c. The reciprocal of a fraction is the multiplicative inverse of that fraction. Remember, when you multiply multiplicative inverses, the product is 1. We're going to look at the definition now of division. It's interesting that division is defined in terms of multiplication. Let a over b and c over d be fractions, where c over d is not 0. Remember that we cannot divide by 0, so it's important that the c over d is not a fraction equivalent to 0. Then a over b divided by c over d is equal to m over n if and only if a over b is equal to m over n times c over d. Again, the division is defined in terms of multiplication. More advanced students can use this idea to actually prove the concept of the invert and multiply rule. Let's take a look at this and see how this works. We're going to take the multiplication statement from the definition of division and then work with it. So we have if a over b equals m over n times c over d, and then what we're going to do is multiply both sides of this equation by the fraction d over c. D over c is the multiplicative inverse of c over d, so that's important in our operation here. So you'll see on this line we have a over b times d over c is equal to m over n times c over d times d over c. So we've multiplied both sides of the equation by d over c. C over d times d over c is the product of multiplicative inverses. And so this is equivalent to 1. So this is equivalent to 1. Any quantity multiplied by 1 is that same quantity. 1 is your multiplicative identity. What this is telling us is that A over B times D over C is equal to M over N. We now have two statements that involve quantities that are equal to M over N. We've got A over B divided by C over D is equal to M over N. And then we have the product statement down here. So what this tells us is that A over B divided by C over D is equivalent to A over B times D over C. Since they are both equal to M over N, they're equal to each other. So this actually establishes the invert and multiply rule. A over B divided by C over D is equal to A over B times D over C. This is why we tell students that when we have a division problem involving fractions, we invert and multiply by the second fraction. So we are inverting the divisor and changing the problem to multiplication. It's very important for students to understand the concepts behind the rules for the operations. If they don't understand the concepts, then they don't really understand what they are doing, and so the multiplication and division operations really don't make sense. We could say the same thing for addition and subtraction. Don't just give the students a rule and expect them to know and understand what they are doing. Plan to give students pictorial or physical examples that they can work with so that they can make connections in their mind as they learn the concepts. This will be important in their development, and it will help them in future mathematics courses.